Hello, Physics 30s. We're going to go and continue our conversation about momentum. So let's get at it. So let's go to our notes here. Well, let's get rid of this. We don't want to see the Snapchat filters I use. And let's look at this page here. This page, I believe, is page 11. Let's talk about collisions. All right? Talked about this yesterday. We're going to lead into this. Like, momentum is all about collisions. Physics 20 was about just leading up to a collision, like before and after, as it's flying through the air and stuff. But now we're actually going to be hitting things and talking about what happens while two objects are in contact with each other, what's happening, right? So that's our goal for today, is to talk about the collision of two or more objects, right? Most of the time it's going to be two. Sometimes you might have three. Very unlikely you'll have 4 or 5 or so. If you get a little bit more advanced, if you ever become like an insurance adjuster or something that has to go investigate collisions to actually see if you're going to get an insurance payout or not, or some kind of forensic investigator, you might actually use more complex mathematics that might involve hundreds of pieces, right? So let's just talk about a few, the simpler ones to start off with, right? So we might have a collision, right? Maybe have two objects come towards each other. There are different types of collisions we have to kind of watch out for. That's what we call just two objects hit each other and they maybe bounce off. So we call a hit and bounce, right? We might have two objects come together and stick together. So, and they come together and they kind of collide and they stick together, maybe like two balls of clay coming together and they meld together as one piece. Or two guys are running along and they tackle each other and they become one afterwards, right? And then the last type of collision doesn't really seem like a collision, but it still follows the same principles, is an explosion. So it starts off as one and then explodes into multiple pieces. And they all follow the same principle, right? The main thing about this, I'm going to just kind of skip past here a little bit, is the main thing about all of these collisions, as long as the system is isolated, so very key, it has to be isolated. Put a little big star here. We'll talk about, like, what if it's not isolated? How do I know if it's not isolated, et cetera, right? As long as it's isolated, and we talked about this, where energy is not allowed to enter or leave the system, and the same thing with matter is not allowed to enter or leave the system. It's all stuck within there. What you start with, you have to end with, right? And if that's the case, then momentum is always conserved, right? Always conserved, right? If the system is isolated, right? So it means the energy has to stay the same and the matter has to stay the same. But that doesn't mean that you can't transfer from one object to another, or the energy can't change from one form to another, right? The momentum can move around within the system. The energy can move around within the system, but it has to stay within the system, right? Now, when we talk about energy, I was just saying, it can transfer from one form to another. So it can go from kinetic to potential. It can go from potential to kinetic. Very specific, like in that explosion, there's no kinetic, right? And then afterwards, we have all this kinetic. So we have all this potential energy, maybe it's locked into that chemical reaction of that explosion. And then afterwards, all of it becomes in this kinetic energy, right? So the energy is allowed to change. And when we talk about energy, we like to talk about, usually we talk about the kinetic energy, right? So if the kinetic energy is conserved, if the kinetic energy is the same as before and after, but again, it could transfer from one object to another. It doesn't necessarily mean that object one has to have the same kinetic energy before and after. It just, the sum of the kinetic energy here and the sum of the kinetic energy here, they have to be the same. If they are the same, then we say the collision that we have is an elastic collision. The kinetic energy is conserved, right? Usually this doesn't happen in like macroscopic things like collisions of cars and billiard balls and curling rocks and stuff. That doesn't usually happen in those kind of scales. But it definitely happens in the subatomic world. And this will pop up later on. This is like our second last chapter. We'll talk about a guy named Compton. And Compton comes along and says, you know what? If energy is conserved, kinetic energy is conserved, we can create a nice little formula. And then we have a formula on our formula sheet. It's not here. I would point towards a formula sheet that would be behind me. And we can use it. Right? So if kinetic energy is conserved, we say the collision is elastic. Right? And if kinetic energy is not conserved, then we say it's inelastic. Right? Now, because we can have these two different types, and both of these can happen in an isolated system, right? In an isolated system, I can have kinetic or elastic collisions. I can have inelastic collisions, right? And because I can have either one of these, it's not a guarantee it's going to be one or the other. I can't really use energy to help me solve a question. It's not allowed. Because I don't know until I actually do the question, like until I get the results, that I don't know if it's elastic and I don't know if it's inelastic. And if it's inelastic, then I can't really use that kinetic energy to help me solve the question. If it is elastic, then I can use kinetic energy to solve the question. And it's actually kind of nice sometimes to do it that way. But you have to know it's elastic before you can do that. So because you don't know if it's elastic or inelastic, we have to use momentum. Right? That's the only way. In an isolated system, momentum must be conserved. In an isolated system, energy, kinetic energy, like we're just talking about just kinetic energy may be conserved or maybe not. Right? So can't really use the energy, but we can use the momentum to solve these questions. So that's just a fun little thing. It's like momentum in an isolated system must be conserved. Okay, so how this works is that in an isolated system, the law of conservation of momentum has to hold true, which also means there's no external net forces acting on these, like external ones. All the forces can be within, like, because that's what's going to happen. You have these two objects inside the system. One is going to come along and hit the other and push it in that direction. And according to Newton's third law, this other object is going to push back the other direction. So we're going to get a force, and while they're interacting, even the smallest amount of time, right? They're still touching for a very small amount of time, and they're applying a force on each other for a very small amount of time. So they are actually changing the momentums. So they're experiencing impulse. This guy's experiencing impulse, his momentum's changing. This guy's is experiencing impulse, his momentum's changing. And we'll talk about that, how that works in a second here. All right, I'll just put it down here in the bottom. Okay, so they're both experiencing impulse. But how does that work for conservation then? This guy's momentum is changing. This guy's momentum is changing. They're both changing. So how can momentum be conserved if they're both changing? Oh, because they're vectors, right? Momentum is a vector. So if this one changes in this direction, because he gets hit that way, so the second object here gets pushed in that direction. Let's say that direction is positive. And then this object pushes back in this direction. They have opposite forces. So if they have opposite directions, because in Newton's third law, one would be positive, one would be negative. And if I go force times time, they're interacting for the same amount of time because they're touching each other for the same amount of time. Wouldn't make sense otherwise. You can't go around and say, I'm touching you for 5 seconds, and the other guy only touches you for 2 seconds. No, that doesn't work. They're touching, right? They're interacting for the same amount of time. So they have different forces in different directions, one positive, one negative, times the same time. So they have the same impulse. The magnitude's the same impulse, but they're in opposite directions. One's technically going up, the other is going down, so they balance each other out and become zero. So there is no change in momentum because momentum has to be conserved. The overall change must be zero. All right? So what I mean by that, let's just let's just write out a little thing down here. So I'm going to draw a little picture, just a simple collision, right? So I have an object, right? I have two objects traveling towards each other. They're going to interact with each other here. So they're actually touching here, right? And as they interact, sorry about that. As they interact, they're going to push on each other with different forces. Like this A, and this is B here. A is going to push B in this direction. You can call it like F, A on B if you want to, right? It's going to push with a force in that direction. B is going to push back onto A, because of Newton's third law, with the same force, same magnitude, but in opposite direction. So those two forces are the same. It doesn't matter if B is much larger or smaller versus the other one. It doesn't really matter, right? B could be a way more massive object. I can just redraw this as B being huge, right? Just a big ball, right? Traveling towards this one. And they're going to interact. Where's B there? B, for some reason, shrunk down to different size. But even though B is much larger, Newton's third law says that these two forces must be the same. Because of the massive size of B, he's going to accelerate at a different rate than A, right? But they'll have the same force, but in opposite directions. And they're interacting, right? And then maybe afterwards, they're going to maybe fly apart, right? So this is just the collision part. This is what we're kind of worried about here. This is the collision part. And then afterwards, B might fly off this direction, and then A might fly off in that direction or something. Doesn't necessarily have to be that, because maybe B would actually continue moving forwards, right? Because of how massive it is, maybe it just slows down a little bit. Maybe the acceleration isn't enough to make it change direction completely. That's okay, right? Now, what's happening in between here, because they're interacting for a very specific amount of time. There's a very small amount of time there, but they're interacting. If I calculate the impulse on A and the impulse on B, and let's just say this way is positive for now. So the impulse on A would be whatever force is. Oh, it's negative force times time. And the impulse on B is the positive force times time. They would both end up being the same magnitude, because the force and the time are both the same because of Newton's third law, but one is positive, one is negative. They would opposite signs to them. So if I added A's impulse with B's impulse, I would get 0. That makes sense? I'm adding one, but the impulse for B is a negative number, or so A is a negative number, and B is a positive number. Which means that the total change of momentum is 0, because momentum is conserved. Now, how that's going to work out most of the time, we're not going to really do it this way. Most of the time, what we're going to do is we look at this before picture, and then we look at the after picture, right? This is like the change in velocity times mass times of the equation. It's kind of just the before and after. I'm not really concerned what's happening in between, because I can just think before the forces happen and then after the forces happen. What I know about those two situations is that all the momentum, now this is kind of, I'm going to just write this down, where all the momentum, the sum of the momentum before is equal to the sum of the momentum after. I know that's kind of weird how I wrote that up there. But the sum of all this momentum before. So if I added the momentum, not the impulse, but just the momentum of A and B, if I added them together, and then I added the momentum of A and B, let's just put a little prime on it, afterwards, what I would notice is that those two things would add up to be the same number. Right? So that total momentum, the sum of the momentum before and the sum of the momentum afterwards, has to be the same, because overall, like that line in the middle, that collision part, that one about the forces, what this is saying is that there can't be a change. The total momentum cannot change. Right? This is saying that there can be no change in momentum. So that means whatever I start off with, I have to end up with. But the momentums can be in different objects. They can be going in different directions. They just have to add up to the same number before and after. That's it. It's a pretty simple process. Now, if I can find those momentums before, I can use the help to find the after. If I find it for the after, I can find it for before. It's a pretty simple process, but it starts getting a little bit tedious when you start throwing in angles and stuff. So let's try one question and see how this turns out. Okay? So, a steel ball traveling east collides with a steel ball traveling west. Afterwards, the smaller steel ball, the 0.25 kilogram one, is now traveling west. It was going east before, and now it's going west. What's the velocity of that larger ball? It was going west before. Did it bounce back and go east? Did it continue moving forwards? Now, you're thinking, how can it continue moving forwards? Like I talked about it up in that previous one. I'm talking about it now. I don't know if you ever, probably hopefully you didn't really experience this, but I hope you never hit an animal. But if you hit an animal, like usually like a deer or something, it's going to be much smaller than your car. And your car is tons, and your deer is going to be 100, 200 kilograms, or probably less than that, right? And what happens usually, like if you hit a moose, that's a totally different story. But if you hit an animal, it doesn't bounce the car backwards. You just keep on going forward, but you slow down a bit, right? It's just how it works out, and that animal just flies off, right? But because of the mass difference between the two objects, the larger object is going to decelerate, of course, but because of the mass of it, it may not decelerate enough to change its direction completely. It might just slow down. It's not going to slow down, come to a stop, and turn around, unless they're comparable in size. And these guys are comparable in size, so they're probably going to bounce off each other. But we can double check that. So this is kind of laid out a little bit weird because it has this middle piece in here. Usually it's one question, but it's giving me kind of this before and after situation. So before, let's just put the before part right here. I could draw a little picture. I'm not going to draw them interacting because that's this middle part here. I'm not concerned about that. I could solve the question that way, actually. There's a way to do it that way. But most of the time we talk about just the before and after. Okay? So the before, this is before they collide. Let's just say east is positive. Okay? And we got this 0.25 steel ball. I'm just going to put the mass on here. So I'm kind of listing off the givens here. It's traveling east with a velocity of 4.5 meters. Now, I've put in already that east is positive, so I wrote a positive answer number there. Okay. Now, the other ball that has a mass of 0.30 kilograms is traveling west. So its velocity is a negative 5.0 meters per second. Now, I didn't really have to draw the negative there because I drew the arrow. The arrow is the direction. But I want to put the negative in there just because I'm going to use it for the math parts. And I just don't want to forget. I made east positive. This number's negative. Okay. So now what I can do is I can determine the momentum of both of these objects before the collision. So the momentum of this first object is going to be mass times velocity. And I just times them together. Pull up my calculator. What was it? 0.25 times 4.5. Okay, 1.125. 1.125 kilogram meters per second. I can find the momentum of this ball. Oh. Okay, do the same thing. The momentum of this ball before the collision. So it's probably going to be 1.5, but let me just double check. Negative 1.5, but it's going to be Negative 5 times 0.3. 1.5, but negative. Okay, so we got a negative 1.5 kilogram meters per second. Okay. Okay, so now we found the two momentums. So what I'm going to do with these two momentums is I'm going to add them up. I'm going to find the sum of all the momentums. So I'm just going to add up my two numbers. But one of these numbers is a negative number. So I'm going to add this negative 1.5. So the reason we had to worry about it, because when you add vectors, you have to worry about the direction, right? So we've done this before. So this number 1.125 plus a negative 1.5, so like minus in a number, so we got negative 0.375. Negative 0.375 kilogram meters per second. Okay, so now we have our total momentum before the collision. And if I believe in Newton's third law, that these two objects are going to interact with each other and produce the same magnitude force but in opposite directions for the same amount of time, then the changes of their momentum should cancel each other out. One will change in the positive direction, one will change in the negative direction. Everything will add up to 0. All the change will add up to 0. And that, therefore, the momentum afterwards has to be the same. But the objects are changing the momentum. Like B is changing its momentum, A is changing its momentum. So the momentums are kind of transferring between the two objects. All right, so they will have new momentums, but they add up to the same number. All right, so afterwards, let me just find my cursor. Now this ball here is traveling west. So I'm just going to rewrite this one. West being a negative number, so I'm just going to write that down as a negative. And quickly do a little bit of math here, and we could determine the momentum afterwards for this ball to be 0.5, right? I just double check. Okay, yeah, 0.5, but negative 0.5 because it was a negative 2. So this momentum is a negative 0.5 kilogram meters per second. Well, that's weird. Like the momentum beforehand added to a negative 0.375, but now this one's negative 5. So this one has a larger magnitude. How can it have a larger magnitude? It's got to balance out. So that must mean the other ball must be going the other direction, right? Now, if you don't know which way the ball is moving, just put an arrow out there, and then the sign convention that we used right here, boop, that says east is positive, the sign convention is going to fix it for us, right? As long as we do the math correctly, we should be good. So I think the ball is going to bounce back, right? But the sign convention might tell me that the ball's velocity is negative. If the ball's velocity ends up being positive, it's moving east, right? So that's my goal, is to find out what this is. To find out what the velocity is, I'm going to need to know what the momentum of this ball is and divide it by its mass, right? I'm just rearranging P is equal to M times V. Divide the M over. So I got to find the momentum of this ball. I got the mass, it's 0.3 there. I got to find the momentum. So what I know is that if I did add all the momentums up afterwards, so the momentum, the two momentums, let's just call, I didn't call one A or B, but if I add these two momentums, let's call the first ball A, call the second ball B. If I add A and B together, right? If I add them together, I need to get the same momentum from before. So 0.375, negative 0.375. So because of that, now I can do a simple algebra question. I know the momentum of A afterwards, so I can put that in there. So negative 0.5 kilogram meters per second plus whatever B has to be, has to end up being this negative 0.375 number. All right. You'll see eventually I'm going to stop writing the units out so much because kilogram meter per second is just kind of tedious to write out as well. But now I can move the things around here. I can solve for the momentum of B, right, by adding over that 0.5. So I got this negative 0.375, and I'm going to add over this 0.5 that I just got. So I get 1.25. Yep. So we got a positive, because I'm adding over that number, it's bigger, 0.125 kilogram meters per second. Okay, so now we know the momentum of B, because this conservation of momentum stuff helped us find it. Then I can take that over to object B there, the 0.3 mass, the 0.3 kilogram mass, and I can put that into this velocity equation, right? 0.125 divided by the mass, and I can find, see the kilograms cross off there. I know the writing is really small, sorry about that. And whoop, divide this number by 0.3. The ball bounces back at 0.41. How many significance? That's it. Probably round it properly. 42. So it bounces back with a velocity of 0.42 meters per second. Bounces back. So it was going west before, and that's bounced back. It's a positive number here. So according to my sign convention right there, a positive number is east. All right, because I'm kind of all over the place here a little bit. I'm going to just highlight my answer. Cool. And that's it, really. That's all you have to do. Like, find the momentum before, use it to find the momentum, or whatever afterwards, right? Or go backwards in time. Maybe we gave all the after information and use that to help me find the before. Only in isolated systems. All right. If the system is not isolated, this doesn't work, right? And that's it. It's like you're done. You're hooped. You can't really do anything, right? If it's a non-isolated system, right? Just the way it is. It has to be isolated for this to work, right? The next thing, is this collision elastic, right? So how do we figure if it's elastic or not? Well, similar to what we had before. We made the assumption that this is an isolated system. But to figure out if it's elastic, we just have to figure out, is the kinetic energy conserved, not the momentum. Momentum is conserved. I made that assumption. Most of these questions, we're going to make that assumption that it's isolated. It doesn't have to say it's isolated, but we'll make that assumption. And with that isolated assumption, it doesn't necessarily mean that the kinetic energy is conserved. We just have to find out what they are. So what we need to do is find, I'm just going to split this in half here. We just have to look at the before situation. Find the kinetic energy of the two objects. So I could just do that quickly here. I just have to go 1/2 mv squared for both objects. Okay? And then add them together. Put a big plus here. And find out what that answers. And then we do it again. This one, I always think this one's the worst. Like, just a bunch of button pressing here. It's almost no fun. And then we do it all over again for these two objects. 1/2 mv squared, 1/2 mv squared. And we add those together. And blah. And find the answer. Right? We can compare them, actually. We don't have to find the answer. We just compare the two numbers. If they're the same, then it is an elastic collision. If they're not, then it's inelastic. So let's quickly do this. Shouldn't take too long to do. I'll just pull my calculator out. Oh, I wish this calculator... That's close. Okay. So there we go. I've got all the numbers I need on the screen, except for this bottom one here, but we'll deal with that later. So I'm going to do the math on the calculator, and then let's write them down to the bottom there. So the first ball here, 1/2. Oh. Okay, let's get rid of that box there. So on the first one here, 1/2 times mass. 0.25 times the velocity squared. Too lazy to find the square button, so I'll just times it by itself twice. Okay, so the first kinetic energy is 2.53125 joules. Okay, that's the first ball. Then I'm going to do it for the 0.3 ball over here. So the next 0.3 ball is going to be 0.5 times 0.3 as a half times its mass times its speed, not its velocity. Okay, so there's that. Because it's 5, yep. Boom. 3.75. Okay. Even if it did put the negative in there, you're going to square it. It's going to turn positive anyway. So this will be positive. And then we're just going to add them together. Plus, plus, oh, a bit of plus there. I don't want to put plus there. Over here, plus this answer. So the total kinetic energy, even though that they're going opposite direction, remember, kinetic energy is not a vector, it's a scalar. So I don't care about the direction, I just how much energy does it actually have. So the total, the sum of all the kinetic energy on this side is 6.28125 joules. So that is the sum of all the kinetic energy. Before, right? Now we're going to do the same thing over here for the after. Boop, boop, boop. So here are the numbers for the after. So 0.5 times 0.25, half times the mass times the velocity. 2 times 2, 0.5. All right, 0.5. So I'm going to put that here. You already kind of see what's going to happen here. 0.5 joules. This other one's going to have a lot, has to have like 6 or 5 joules of energy, 5.5, 5.7 joules of energy to make this work. But it's going slower. It's not going very fast. It's actually going slower than the other ones. So I don't think I'm going to be able to get that. So let's just double check. Times the velocity, this velocity, squared. I'll have to hit the square button this time. Boom. It's tiny, right? So 0.026, etc., joules. I add them together, and we get this number plus 0.5. There you go. Oh, I could have just done that in my head. I don't know what I was thinking. Maybe because it's almost midnight. Okay, so 0.526 joules. Now I'm going to look at these. Let's doop, and compare the two numbers. They're definitely not the same, right? If they're not the same, it's an inelastic collision. So the kinetic energy is not conserved. I'm going to write that down. Kinetic energy is not conserved. Conserved. Because it's not conserved, this is inelastic. Or non-elastic? Inelastic is a better word for that. Inelastic collision. Okay, now I mentioned this before. Like if I scroll up here, 90% of the time, you're going to get an inelastic collision. Like you see, elastic collisions do not occur at macroscopic levels. There's always some distortion of objects. The objects will distort themselves, like they'll squish in and then maybe they don't bounce back completely, right? They kind of deform a bit. It's not like you didn't lose the matter. It's still there, but now the energy got stored into that object as potential energy because it's squished in and didn't really pop back out, right? Or that potential energy exploded into kinetic energy. So the majority of the time, it's probably a good safe bet is to say it's not elastic, it's inelastic. Otherwise, you can try to confirm it by doing the math. Now, they might get really close, right? But to be perfectly elastic, it's got to be exact, right? It's just how it works out. So even if they're slightly off, it's inelastic. All right, let's try another. So here's another one here. We got a guy kind of just sitting here in a boat. He's going to throw his harpoon one way And because he throws his harpoon one direction, he's going to have this recoil backwards. It's like if you ever shot a gun, just that recoil, just the bullet, the tiny little bullet should go really fast, goes off one direction, and you get that recoil backwards. Hopefully, that gun firmly into your shoulder, and it kind of recoils backwards, right? Or if you have a pistol, it kind of recoils backwards there. Or I don't know if you've ever done this. You might be on a boat, and just a small little boat, and you chuck a bag off that boat. The boat's going to float backwards because you kind of pushed off one direction, right? So we're going to do the same thing here. So this harpoon, it's a relatively small harpoon. He's going to chuck it as fast as he can. He's a much bigger guy. He's got the hunter, the 75 kilogram hunter, in this 10 kilogram kayak. They're kind of attached together, so we're going to have to treat them together. He's going to shoot this harpoon off in one direction. What will the velocity of the kayak and hunter be immediately after it's released? So, before and after. So what I'm going to do, just kind of split this down the middle. I got the before on the left side. I got the after on the right side. So let's see. We've got the hunter being stationary in the kayak. So that's going to be meaning that his velocity is 0. His mass right now is everything added together. He's just holding on to that harpoon. He's 75. The kayak is 10. So technically, the mass of everything is 85.72 kilograms. That's kind of beside the point, because what's 0 times everything? 0. I'm going to sneeze. Sorry. All right. So the momentum of this kayaker before this happens is 0 kilogram meters per second. That means the sum of all the momentum, because there's only one object, they're all together. If you want to do the math for each individual piece, you can. But 0 plus 0 plus 0 is just going to be 0. So everything adds up to 0, which means that everything afterwards has to also add up to 0. Okay, so let's look at afterwards. So we have two objects here. We have the kayaker, who is 85 kilograms, because the kayak plus the hunter. So those are the two things together. And then we have the harpoon, kind of shooting off in this direction, 0.72 kilograms. All right, what we know about the velocity of the harpoon, we also have a sign convention. It says your right is positive, that the velocity of the harpoon is 12 meters per second, which also means we calculate its momentum by going mass times velocity. So let's pull out our calculator here. 12 times 0.72. Bam. 8.64. Positive. Okay, cool. So now we know the momentum of the harpoon afterwards, but everything's got to add to 0. Doesn't really work when the beard's fake. Everything's got to add to 0. So we could just use logic and say, okay, that's positive 8.65. That means the kayak hunter must be negative 8.65. It means, oh, it's just going backwards. Yeah, it makes sense. So they're going opposite directions. If you want to use a little bit more mathematical about this, you can say that if I add, I don't know, this is TF, and this says HF. I don't know what that, harpoon final, and this is total final, or whatever. It's VT. Okay, so let's call that. So this is a harpoon, and the one that we're looking for here is T, because I don't know that one. If I add those two things together, I should get 0, right? Because of this. So everything that added up to 0 beforehand, everything adds up to 0 afterwards, conservation of momentum. We're making the assumption, we have to, for the only way for this to work, we're making the assumption that this is isolated. Okay, so we can put our numbers in here. We could just, actually, we just rearrange this and say that, oh, PT, the momentum of the hunter and kayak together, is just equal to negative pH of the harpoon. Oh, okay, so that means this is negative 8.65. Right? Okay, now we know the momentum of the harpoon and, or not the harpoon, the kayaker, the hunter and the kayak together. I can now use that to determine the recoil velocity here. I'm kind of running out of space here. I wish I planned this out better. I'll just have to write it over here. So to find the velocity, I'm going to take the momentum divided by the mass. So the momentum is negative 8.64 kilogram meters per second divided by the total mass minus the harpoon, 85. And yes, oh, I had this number right here, divided by 85 there. Boom. 0.102. How many sig digs do I need? Oh, don't want that. Where's that? There we go. 2 sig digs. 0.10. Negative 0.10 kilograms crossed off meters per second. What does the negative mean? Well, I go back to my sign convention. You can see over here the sign convention says that positive is right, so a negative must mean this is left. So I'm going to get rid of the negative. And write the left down. That's it. It's a pretty simple process, right? Just before and after, that's all. So there's a few questions that you guys could try. I'm just trying to figure out where to stop here. Eventually they start just kind of repeating. Ooh. So if you want to, you could try it. Like it's, I don't know how much time is left in class because you wrote a quiz. This is about 40 minutes so far. You could try these other questions here. But when you get to this ballistic pendulum, I'm pretty sure if you really think about it, you can try to figure it out. That's on page 19. Just kind of stop. Right? We'll come to this ballistic pendulum when I get back on Monday. Hopefully, cross my fingers, I'm back on Monday. But all these other questions are very similar. Before and after. Watch out for positive and negatives. Sometimes they bounce off each other. Sometimes they collide and stick together. Sometimes, like this first one we just did, they just explode. But momentum, if we assume that momentum is conserved in all these cases, that this is an isolated system, it's whatever the momentum is before is equal to the momentum afterwards. I don't think any of these are funny questions. Ooh, this is a fun one. I like this one. That's a hard question, but try it out. I want you to try it. You have the rest of the class, and if you want more questions, I believe I have them printed off somewhere up in the front here. I'll ask whoever's the sub to hand them out, so you have some more questions to do. And I'll see you. You have lots to do, I think, right now. I'll see you on Monday.